Last time what we saw was about the least common multiple. So this is our objective. This is what we wanted to try and do, but we just talked about how to what actually is the least common multiple. That is what we talked about last time primarily. So first I would like to remind that, and then we will go on to actually try to find the order pairs that we're looking for. Okay, so for the least common multiple, okay, anybody remembers more or less what is the least common multiple that we talked about last time?
Can I answer?
Yes, of course.
So I'm pretty sure the least common multiple is the less number you can use that is a multiple of that number. So for an example, you have 6 and 12, correct? So the least common multiple of 6 and 12 would be 2. So 2 times 6 would equal, or no, 2 times 3 will equal 6, and then 2 times 6 will equal 12, and I'm pretty sure that's the least common multiple.
Again, which happened last time, you're having you're confusing it with the least common divisor. Okay, so the least common multiple that we're trying to find here is the first number that both of those numbers that you said can divide. Okay, so it's not the smallest divisor. So what you said is that when we have 2 and 6, that 2 can divide both of these guys. That's what you said, right? But that's not what we're looking for here. The idea of the least common multiple is the first number that both 2 and 6 are able to divide. Okay, that's what we're trying to find here. That is what is the least common multiple. It is the first integer that is divisible both by 2 and by 6. Okay, so we actually saw some examples last time about that. Let me make a quick review. So for example, in this case that we're looking for the least common multiple of 12 and 16. See, we're looking for the first time that the number appears in the multiplication table of the number. Okay, so for example, here we have 1 times 12, which is 12, 24, 36, 48. Okay, so 12 divides 48. And then also we have 16. So 16 also divides 48. Okay, so 16 also divides 48. So the first number that both 12 and 16 can divide is 48. That's the least common multiple. Okay. It is not the least common divisor that we're talking about. So the smallest number that can divide those two guys. We're looking for the number that both of these can divide. Okay, does this make any more sense? Any better now? Okay. Okay, let's do some of these examples, just so that we can get again a feel of it, because we're going to need it later. Okay. So anybody want to help me with, let's say, this one?
May I answer?
Yes, for this one here.
So for 2 and 6, the least common multiple would be 6, because the first number is 6, and when you add, or not add, but when you multiply 2 3 times, you get 6, and that is the least common multiple that both numbers have.
Yes, okay, very nice. Essentially, you see that 6 appears here in the multiplication table for 2, and of course 6 immediately appears in the multiplication table of 6. So this is the smallest possible number that is divisible both by 2 and 6. Okay, thank you. All right. And okay, and let's try also this one, just to remember it.
May I answer again?
Yes, absolutely.
So for and 6, when you multiply 4 by 3, you get 12. And when you multiply 6 by 2, you get 12 also. And that is the least common multiple because that's the first number that both numbers have in common.
Yes, yes, very nice. This number that you mentioned appears in both of the multiplication tables. So we have 4, 8, 12, and then we have 6, 12, 18. So the first guy is 12. That appears in both. So 12 is divisible by 4 and by 6. Okay, so that's the least common multiple. Okay. All right, very good. So what we talked about last time was that what happens when the numbers get bigger. Okay, how can we find a nice method for the how can we find a nice method to extract the least common multiple when the numbers are big? Okay. So, and we had a discussion about it. And unfortunately, I don't have the time to go through all of this again. But the gist is that a nice technique to find the least common multiple would be to find the prime factorization of the number that we are working with, and then we just choose the highest exponent that occurs for each prime number. Okay, so just going to show what we're doing with this one. So for the least common multiple of these two numbers, what we would do is we would break it down into the prime number factorization, and we would just try to see what is the highest of the two exponents that are there. And then we would just choose the highest exponents in these two cases. Okay. So this is what came out of the discussion that we made last time. Okay, this is just a quicker way to find the least common multiple of two numbers. Okay, you just find the prime factorization, and then you choose the highest degree of the prime numbers that appear there in the power. Okay, so we talked about the least common multiple. We're gonna need it later for our objective. It's very important. And then we briefly talked about ordered pairs. Okay, so an ordered pair essentially of two numbers. An ordered pair here is a pair of numbers where the order is important. Okay, so where we're trying to find ordered pairs of numbers, then we consider these two to be different than each other, different elements than each other. Okay, so, and then we saw an example about it. Okay, so I'm just trying to make a small recapitulation of what happened. So okay, can somebody help me with this one? Let's see. Can we create some ordered pairs from these numbers here? We did this exercise last time too, but I just want to refresh your memory in this one. So can somebody help me to find the ordered pairs that I can make with these numbers? Anybody? Just you can type them in the chat box if you want. For example, a possible pair that I could make here would be 1, 2. A possible pair that I could make from this. Can you tell me a few more? You don't remember about talking order pairs? Yeah. Well, what we said about ordered pairs was that the idea is that when we have a pair, it is quite different. If I gave you this point, for example, it would be quite different than this point right here. Okay. So when we have a bunch of numbers and we create ordered pairs, then we are interested in creating all possible pairs of these two numbers. But the order which we put them is important. So for example, this pair that I could create is different than this pair. That is what we're trying to do with the unordered pairs. We're just creating pairs of numbers, but the order is important. So this element is considered different than this one. Okay. That's the gist of the ordered pairs. So with this idea, if I wanted to make ordered pairs, yes, perfect. 2, 3 is another one. Yes. 3, 2 is another one. Very nice. Yes. 3, 1. 1, 3, which is the mirror. Very nice. Are we missing something? Did we say 2, 1?
2, 1.
2, 1. Yes. Great. Thank you. We're getting to 1 too here. And we are also allowed to choose the same element twice. Okay, nobody restricts us on that. So actually, these are very nice ordered pairs too. Okay. Yes. Yes, Angelina. 1, 1, 2, 2, and 3 are also ordered pairs. Okay. So those are all the ordered pairs that we can make. All right. And with this in mind, we also have the idea of unordered pairs, which essentially means that this time we are considering this pair to be the same as this pair. Okay. This is the only difference when we create unordered pairs. So these are considered the same pair, and we don't care about pairs that contain the same entry in both elements. That is the difference when we talk about unordered pairs. Okay. So that's what we briefly said at the end. So let's try now to make the unordered pairs of this group here. So 1, 2 is one possible. Yes. Next.
1, 3.
1, 3.
And 2, 3.
And 2, 3. What about 3, 2? Why isn't this possible here?
Because it doesn't follow the necessities to be an unordered pair, because that is the same as 2, 3.
Yes, this is considered to be the same with this one, because now we care about unordered pairs. So he goes away. We don't write him down. And we also don't write down all of those guys. They are not considered unordered pairs. So we are left with these 3 choices. Thank you. And the question that I left you with last time was that how can we find, if we have the ordered pairs, how can we find the unordered pairs? What is the idea? Yes, Angelina. When we have a bunch of numbers like this, we are interested to create pairs, but we have the ordered pairs, in which case we're going to write all of those that we wrote here, in which case we care about every possible pair that we can create with those numbers. So it's 1, 2, and 2, 1, all the possible pairs that we can create. But when we're interested in unordered pairs, then we are not going to include all the mirrors of those. So the unordered pairs is that I care about him, but I don't care about his mirror. So I'm gonna list him only once this time. That is the difference. Okay, so we are not listing this guy, we're not listing this guy, and we are not listing this guy. And these are not considered unordered pairs, okay? So these are the unordered pairs that we can make from this set. Only those choices, okay? That is the difference between them. So the question that I asked you at the end of last session is that assume that you have found the ordered pairs, how can we find the unordered pairs? Did anybody maybe think about that during last week?
Do you mind if I answer?
Yes, tell me.
So basically, you can either choose one of the pairs. So for an example, if you have 1, 3 and 3, 1, they're ordered pairs, right? So you can pick either one. It's just that it really doesn't matter. It's just you can't use the same numbers twice because they're the same, and you don't need to have that for the unordered pairs, basically.
Yes, but how can you figure out the number of how many they are? That's very interesting. Like, what do we have to do when we have all of the ordered pairs here in order to figure out what are the unordered ones? So these are all the ordered ones. Which ones would you throw away?
Is it okay if I answer?
Yes.
Okay, so like you can remove the ordered pairs that like are reversed, I guess. So like
Mm-hmm.
if you have 1, 2, and 2, 1, you can erase 2, 1 because you already have
Yes.
and you can
Okay.
erase the ones that have like the same number twice, like 1, 1 or 2, 2.
Yes, those are not considered unordered pairs. I think that's more or less what Arman said. That's the basic idea. Okay, we just cut all the mirror images and we remove all of the ones that have the same number twice. Okay, very nice. But let's try to be a bit more careful. Okay, so here we saw, for example, that the ordered pairs that we found were 9. We found 9 ordered pairs. Okay. So as you said, we have to subtract however many are the ones that have the same number in both entries, however many they are. In our case, there were 3, right? So we subtract 3. So then how can we find the number? How can we find the number of the unordered pairs from this? So what can we do to this number to figure out how many are the unordered pairs? So essentially we have this, we start with this 9 here. We remove all of the ones that have the same number in both entries, and we are left with those here. How can we immediately understand how many they are? How many are there unordered pairs just from this one? What do we do with those? So you see that each of the pair that is here has its mirror, right? So that means that if we have 6 elements, 6 pairs, how many are the unordered ones? 3, half, right? That is the big idea here. That if we go ahead and take the ordered pairs and we remove all the ones that have the same entry in both cages, then we can just divide by 2 and we find the unordered pairs. That's the big idea. So this would be 6 over 2, which is 3. Okay, so that is very important and we're going to need it later. If we want to find how many unordered pairs we have, we just have to subtract the pairs where A is the same as B, so where the 2 entries are the same, and then we divide by 2. Okay. Because in a lot of the examples that are going to follow, we're going to first find the unordered pairs. We're first going to find the ordered pairs, and then we're going to deduce how many are the unordered pairs. Okay. So does this make sense? Okay. So now we can go ahead with all of these preliminaries. We can go ahead and start asking the actual question. Okay. This is what we wanted to do when we started. We are given a specific least common multiple, and we want to find all of the ordered pairs that have this specific common multiple between them. Okay. And we will get there. We eventually are getting there. But first, I want to try with smaller numbers. I want to show you what we're trying to find. Okay, first. So let's start with this exercise right here. We are looking for all the ordered pairs where the least common multiple between the two numbers is specific, is 6. Okay. So let's see if we can find some of them. Can you tell me pairs of numbers that have a least common multiple of 6 between them? Try to think of some examples.
6 and 12.
Okay, 6 and 12 is a pair. Let's see. Let's see if that could be the least common multiple. So again, you are thinking in terms of the list of the greatest common divisor, of the least common divisor or something. Because the least common multiple of these two is going to be bigger. Okay, 6 is the smallest that divides both, but we're interested in the number that these guys divide. Okay. So let's see. Okay, Abhit is writing some pairs. Let's look at them. So we have the pair 1 and 6. Okay, that was proposed. What is the least common multiple of these two numbers, of 1 and 6?
6.
6, right? Exactly the one that we want. Which means that this 1, 6 is one of the pairs that we're looking for, because we're looking for all of those pairs. Okay, all right. So very nice. So I'm writing it down, and you will agree with me that since we are looking with ordered pairs, for ordered pairs, this is a very valid answer as well. It's mirror image, right? Because we're looking for ordered pairs. Okay, next, others. I think Abhiti wrote some more.
2 and 3.
2, 3, nice. The pair 2, 3 is correct, because what is the least common multiple of 2 and 3? It is 6. And again, let me remind you the technique that we have. To find the least common multiple, we write the two numbers prime factorization. Here they are both prime, so we don't have anything. We just choose the highest power, okay? I will actually demonstrate it with a bigger number later. So the least common multiple of 2 and 3 is 6. So this is a very valid pair, so we're keeping it. Nice.
I have another pair.
Yes.
2
Tell
and
me.
6.
2 and 6, let's see. 2 and 6. So what is the least common multiple of 2 and 6? It is, of
6.
course, 6. Very good. So 2 and 6 is another very valid pair. Nice. And the mirror image. Okay. Okay, let's see. We have 3, 6 you're proposing. Very good. And 6, 3. Very nice. Very good. Okay. Are we forgetting anything? Three, 2. 3, 2 is right here.
3, 3.
3, 3. Let's see. We discussed this last time. The least common multiple of 3 and 3 is itself, actually, if you think about it, right? Right, because 3 is the first number that 3 can divide, and 3 is also the first number that 3 can divide. So the least common multiple is itself. And generally, whenever you want to find the least common multiple of the same thing here, it is going to be itself, right? The least common multiple. So 3, 3 is 6 and 6. Perfect. Thank you. That's the idea we're missing. It's actually, we just pick the least common multiple in both pairs. Nobody forbids us to do that. Of course we can do that. Why not? Perfect. So this is the remaining pair. Those are all the pairs. Okay, good job, guys. Very nice. Let's see if we missed something, because I think I listed those. Yes, I listed those. Okay. So, so here are all the cases, all right? And this is the problem that we're trying to solve. We are trying to find, for whatever number I give you as a least common multiple, whatever number I give you, the problem we're trying to solve is to figure out all of these ordered pairs for each problem, okay? This can be significantly harder if I give you a very large least common multiple. That's why we are building up to it, okay? Okay, so now let's look at what these guys have in common, okay? So I want to make some comment here about those pairs, what they look like. So I'm gonna change the color they have. Okay. So let's notice what these guys have in common, okay? They are all multiples of 6, you said. Well, factors is the better word. I like it. Factors, right? Because Angelina, the multiples of 6, are 6, 12, 18, right? They go up. What you mean was divisors. Yes, nice. Okay. So all of these are composed by, as you said, divisors. Okay. But let's take a closer look and see what happens. Okay. Because I'm going to try to write this in a slightly different format. Okay. Let's see. So can you agree? Just take a look at this for a second. Can you agree that I could rewrite the pair in this format here? Can you agree that I could write it like this? Right, this is the same pair as it is above, This is exactly the same pair, but I just wrote it wrote these numbers slightly differently. That's all I did. Okay. So can you agree that I can rewrite it like this? Okay. Nice. But maybe I can do the same here. Here I have the mirror image. Right. So maybe I can do something very similar here. I can just go ahead and mirror the process that I did. Can somebody try and write this pair in a similar form? So we would like to do something similar. So I want you to rewrite 2. Let's see, at heap says 2 squared and 2 to the first. Says Evelina. Yes, at heap has the right decomposition that he's writing there. What do you mean by 2 squared, Angelina? That you wrote. Yes, that's fine. Don't worry about it. No problem. We are essentially trying to rewrite these numbers in a similar form to this. And as at heap mentioned, the way I can do this is I write 2, I can write it as 2 to the first power times 3 to the 0 power. We are just trying to rewrite all of those numbers in some similar form to this, okay, by using 2 and 3. That's what we're trying to do. Okay, so I'm going to write this as 2 to the first power times 3 to the 0 power, because this is 1. And then 6, I can write it like I did before, 2 to the first power times 3 to the first power. Okay. Same for the mirror image, of course. I'm going to do it because there is no difference. Yes. Yes, nice. We just reverse it. Perfect. Thank you. All right. Yes. Okay. Very nice. Let's continue. Let's keep it going. Okay. So at heap now is doing actually the next one, I think. Yes. So at heap is now decomposing 3. He wrote 3 as 2 to the 0 power times 3 to the first power. Okay. And then a 6 is the same. And of course, the mirror image, I can rewrite it like this. Very good, very nice. Okay, somebody else wants to try to decompose this maybe?
May I try?
Yes.
So the first one for 2 would be 2 to the first power multiplied by 3 to the 0th power. And then for 3 would be 2 to the 0th power multiplied by 3 to the first power.
Perfect, thank you. Amazing.
And you're just going to reverse that for 3.
Yes. For
Yeah.
the mirror pair, I'm just going to reverse it. What did I do? To the first power. Okay. And for 6,6, which is the last order pair, how can we rewrite that in a similar form?
May I try?
Somebody else was, I think. Who did I hear? Yes.
Me.
Tell me. Yes.
Sorry. Okay. Sorry. So 6,6 would be 2 to the first power times 3 to the first power, and the same thing on the other side.
Perfect.
6.
Great. Thank you. For Angelina, you could do that, but I have a reason that I'm doing it this way. I have a reason. I just want to show you here that if we are careful, we see that actually all of the pairs that we found have a very specific format. All of the pairs, right? So all of the pairs that we found have this specific format. They have 2 to some exponent times 3 to some exponent, and same thing goes for the other pair, part of the pair. Okay, for all of them. Okay, and this is interesting. This is what we're going to use to create our method for solving this problem. We're going to use this observation. Okay, so as we can observe, all of the ordered pairs can be written like this. Okay, so and I think I have yes, I have actually written this here. this is exactly what we did. Okay, we figured out that every single of those pairs can be written in this form. Okay, so all of them can be written in the form 2 to the x power times 3 to the y power, comma, so sum power of 2 times sum power of 3, comma, sum power of 2 times sum power of 3, all of them. Okay, and we have to see actually where does the 2 and 3 come from, and why is this true? Why does this happen? Okay, and how can we use it? But before we get into why this happens, I want just to take this example and make some observations on this example. Okay, for first. So that's what I'm gonna start with. Okay. So let's take a closer look into this, into specifically only the pairs. Okay. So let's look at that. So if you notice, actually, this here, the 2 and 3 is actually the prime factor decomposition of 6. Okay, the prime factorization of 6. And I want to ask you some questions about this. So all I have done here is I have taken all of the ordered pairs, I have written them differently, and now we are looking at those pairs. Okay, written differently. Okay. So this is the question to you. From what you can observe at this point, what are the possible values for x and s? So x and s is, as you can see, is the exponents for 2 in those pairs. So what are the possibilities that we have here? Yes, thank you, Abhiti. We only have 0 and 1, if you notice. Okay, in all of these pairs, the exponent for 2 in every, it's only 0 and 1. Okay. And what about y and t? Same question.
1 and 0, same thing.
Yes, it is the same thing, y and 0. Okay. So as you can notice, we actually have very limited choices that we can use for those exponents. We have only 0 and 1 to use. Okay. Can you see it now that anywhere x and s are simultaneously 0? Can you find any pair that does that? So, no, right? There is no pair that has 0 in both of these.
Because
Right.
that would end up as 0 and a 1 equals 6.
Yes, that is the basis behind it. Very good. Very nice observation. The reason why this happens, and I wanted to get to this later, actually, but since you're bringing it up, we might as well bring it up. Okay. There is no pair where you have 0 and 0, because if that were the case, then you would have 2 to the 0 times 3 to some power, and 2 to the 0 times 3 to some other power. But this is actually 3 to some power, 3 to some power. So you see the least common multiple of this would be 3 to some power. It wouldn't be 6. If we put 0 in both of these, we are taking away the 2 from the prime factor decomposition. Okay, so the least common multiple is no longer 6. Okay, does this make sense? Yes, because this is not simple. I want to make sure that it makes sense to you. Yeah. Yep. Okay. All right. Nice. Nice. So we notice, we observe that they cannot be simultaneously 0 in any of the pairs, and we understand why. This is what Armand said. If you have in both cases 0, you're taking away the 6. Actually, you don't have any more. This cannot have a least common multiple of 6 because there is no 2 anywhere. So 2 has to exist in one of the two pairs always. Okay. So very nice. So now what I'm going to do is I'm going to take it a step further. So we had started with the pairs. We wrote them down into this nice form. And now I just want to look at the exponents. So instead of just looking for all of this, I'm going to focus on the exponents, only on those guys. Okay, that's what we're going to do next. So let's look at them. So what I'm doing now is I'm only keeping the pairs of exponents, just so that you can see what happened. For example, in this case, where we have these exponents, I'm just putting this together in a pair. That's all I'm doing here. Okay, I'm only caring about the different pairs of exponents that exist. Okay, so instead of having all of this big pair, I'm putting together the exponents for 2. Next to it, I'm putting all the exponents for 3. Okay, that's what I did here. So let's look at those and let's see what we have. Again, by what we did, by what we saw, there can never be simultaneously 0, never, anywhere, as you can see. We explained why. But also we see that the only cases are 0 and 1. All right. We're just making observations now. Okay. So this I want to actually talk about. Yeah. So you see that for x, y, there are only 3 possible choices that we have here. This one, and this one. So for the red pairs that are the powers of 2, we have only 3 possible cases, right? All of the others are repeated. And the same goes for the green pairs. We have this green pair, and this green pair. Then they are repeated, okay? So we have 3 choices for the exponents of 2, xs, and we have 3 choices for the y's, okay? And that gives us 9 ordered pairs, okay? That is the idea of this method. Because why 9? Why the product? Because if I have one choice for this one, then I can make, if I want to put them together, I can do this in 3 pairs, okay? So I can create all of these guys. Okay. So this is 1 choice, 2 choices, 3 choices, okay? Same for the next one. Another 1 choice, another 2 choices, another 2. Same for the last one. 1, 2, and 3. So we have 3 choices from the first, plus 3 choices from the first, plus 3 choices from the sixth. So that's 3 times 3, which is, what the hell did I write here? 9 ordered pairs. Well, yeah, apparently I can't do math. That should be a, 27? No, that doesn't make sense. What am I missing? Oh, nothing. I'm just losing my mind. That was fine. Don't worry. I'm losing my mind. Don't worry. That's fine. So 3 plus 3 plus 3 is actually 3 squared, which is 9. So 9 ordered pairs. That's fine. Okay. So so this, that what you saw now, all of the process that we did is actually what this method is about. Okay. We are essentially going to be trying to look for these forms, for these possible forms that you can write the ordered pairs. And then instead of counting the actual ordered pairs, we're going to be counting those easier to make pairs. This is the idea for the method. It's gonna make more sense later. Okay. So so let's try to do this again, this process, but this time we're going to do it with a slightly larger least common multiple. Okay, slightly larger. So we have 12. So what can we do here? Essentially, we would like to find all of the pairs in the same sense that we did it beforehand. So we have them here, okay? So the least common multiple of 1 and 12 is 12, of course, right? So we are doing all of the process that we did for the last example, but in the last example we had 6. Do you remember, right? In the same way, you can find all of the ordered pairs that we're looking for. Okay. And again, if you notice in the example that we did with the 6, we had like 1 6 6 1 2 6 6 2 and so on, right? And at the end we had 6 6. Right? So in the same fashion, here we have 12 12 at the end, and we also have for every other pair there is the mirror image. Okay. For every other pair there is the mirror image. Okay. So now let's get deeper into this too. Okay, so let's try to make the pairs on our own. This is the same idea as before. When we had the least common multiple to be 6, when we had the least common multiple to be 6, then 6 has a decomposition of 2 to the first power times 3 to the first power. And the pairs were of the form 2 to the x times 3 to the y, 2 to the s times 3 to the t. Okay, this is what we did for 6. But here we have the same, exactly the same factorization, except for instead of a 1 that we had in the case of 6, here we have a 2. Essentially, that is the only difference. So let's see how this affects the pairs. Okay. Let's see how this affects the pairs. So can you try to write these pairs that we have here in this format again? Exactly like we did with 6, but now we're doing it with 12. So does somebody want to try? So let me do the first one. Yes, yes. Oh, I'm sorry. I gave it away. Never forget that. Let's go.
So for 112, you want to use 2 to the power of 0 multiplied by the 3 to the power of 0, and that will equal 1. Now you want to do 12, which is going to be 2 to the second power and 3 to the first power, which
perfect. Right here, right? And then we have the mirror image. All right. So in this fashion, we can do the same thing. Let's actually try one slightly different. Let's try, somebody want to try this one?
I can do it.
Yes.
Okay, so that would be 2 to the second power and 3 to the first power. Comma 2 to the first power and 3 to the first power.
Perfect. Okay. So as you can see, it follows the same format again, but this time we have more freedom on the exponent for 2. In the last example, we only had 0 and 1. Let's see now what we have. Okay. So
wait,
you notice,
wouldn't it be 2
yes,
to the second power and 3 to the power of 0, not 3 to the power of 1?
for which one?
See how it's 3 to the first power, because that will
Absolutely.
equal 12.
You are correct. Thank you. Nice catch. I would never see that. It's a 0 there because it's 4. Yes, it's the 0. Thank you. Nice catch. Okay. So so essentially we have again this way to write them. Don't worry, Pity. I missed it too. So if you notice now, we have again, if you only look at the exponents for 2, we have 0 2 and 0 1 here. Okay. And in the same sense here we have 2 0 and 1 0. So if you group all of this together, you will see that the choices for the pairs are all those here that you see. Okay, I have just grouped them up for you. Okay. These are the possibilities for the pair x comma s, right? For the exponents of 2. If you go ahead and try to group these up, okay, and keep going, you are going to arrive at these cases. There is no other case here, okay? So since we have 5 cases for the exponents and 3 cases for the exponents of 3, then we're going to have actually 15 ordered pairs. It is exactly the ones that we found before, but I'm interested in why this happens, okay? Because see, we found all the cases for this pair. These are 5 cases. Found all the cases for y and t. These are 3 cases. And then, as we saw in this diagram here, in order to choose them all together, we're going to have to multiply how many pairs we have for the exponents of 2 times how many we have for the exponents of 3. Okay, so so we have actually 15 ordered pairs. But what we're interested in is to try to find a good way to figure out the pairs, those pairs. Because you agree, if we figure out those pairs, then we can just multiply the numbers together and we'll get how many are the ordered pairs. It's exactly what we want, right? So that would be a good way to calculate these pairs, to calculate all of these possibilities easily, instead of having to dig into the number and pull out the pairs ourselves. That would be a better way to do that. So let's take a look at the possible pairs for x and s. Okay, so all I'm doing is I'm taking the pairs for x and s that I have here, and I'm taking a closer look at them, okay? So what do you notice about all the possible cases for x and s, right? These are those 5 cases. We can group them like this, okay? So let's answer this question. In all of the cases that we had back here for the possible exponents, in all of these cases, 2 has to exist in one of the two places always, as you can see. Why is that? This is something that Armand said earlier. Why does 2 have to exist in both of the cases? Excuse me, in at least one of the pairs.
Because you can't have a 0 and a 0 pair, so you have to at least have a 2 in order for it to become a 2 in the problem.
Yes, but why, for example, don't we have 1, 1 here? What is the difference with the last problem? See, 1, 1 doesn't exist here. So the idea is that if we had x and s to be, let's say, 1, 1, then if you try and put it in this place, you have 2 to the first power times 3 to the y. It is again the same thing that we did. 2 to the first power times 3 to the t. And this is going to be 2 times 3 to the y, 2 times 3 to the t. This pair cannot have a least common multiple of 12 because it cannot create the 4 that is needed. It cannot create the 2 squared. Okay. So this is basically the idea that Armand said. The reason why there has to exist this exponent in at least one of the places of the pair is because otherwise we wouldn't have the correct least common multiple. We would have a smaller least common multiple. Okay. So in all of the pairs, you see that 2 has to exist at least in one of the positions, okay? Or in both. Okay. So that's the first observation. And again, as you notice, we have 2, 2, and we have a mirror here. We have the mirror images. Right? This is just an observation we're making now. Okay. So all of the possible pairs of exponents for the powers of 2, which is x, s, are in this format right here. We have 2, 2, and then we have mirrored images of the rest. Okay. So that's what we have. Which means that instead of just looking at all of them, so instead of looking at all of them, I can just look at the left side of the mirror, essentially. Right. So my pen is not working. I'm sorry. Never mind. Okay. So what we're trying to do now is we're trying to find an easy way to calculate these pairs, okay? And we're just making observations. We're seeing that I have this pair that is 2,2, and then I have mirror images, okay? So I'm only going to look at those guys here, because then I have their mirrors. Next to them, there are their mirrors, I know it. And 2,2, okay? So all that we need to figure out now is how many of those pairs occur. So how many ordered pairs can you make such that 2 is in this position, and here you have only smaller numbers than 2? That's what we're trying to figure out. Okay. Okay, so all that we are allowed to have here, we are not allowed to have 2,2 because we took it away. Okay. So here we are only allowed to have smaller numbers than 2, which is the 0, and another smaller number, which is 1. Okay. So we have only 2 possible choices. Okay. So I want you to understand the process that we took. We first saw all of the pairs that we had. So we had all of these possible pairs. And 2,2. We had all of this, and then we're trying to figure out how can we understand, how can we find these pairs without having to go through the numbers, okay? And we're noticing that we can find these 2 pairs, double this number for the mirrors, and then add 1 for this guy. Okay. So so in reality, actually, let's see if I want to do this. Yes, okay, let's see. Here, this is just a conceptual question. What I'm asking is, how many pairs can you make here of these numbers such that the question mark is smaller than 3? How many possible pairs do we have of this form? This is slightly unrelated to the problem, but you will see where I'm going with this. So can somebody try to tell me this? If here I am allowed to put numbers that are 0 or bigger than 0, integers, then how many pairs can I make such that this is strictly smaller than 3? How many pairs can I make like that?
You can do 1 and 3.
I can do 1, 3, yes. Any
and
other?
1.
Any other? Well, now I'm not caring about the mirrors because, as we said, the mirrors, I know they exist there. That is true. I'm only caring about this format. So first can be 0, 1, or 2. Okay. All the smaller numbers than 3. So I have only 3 choices, right? 3 choices. Okay. So out of all of this discussion, what we're getting is that we could figure out the possibilities for the pairs X and Y without digging into the number, how many they are. It is this idea here. All the possibilities for those exponents are 2 squared because we have 2 possibilities times 2 for the mirrors, right? And then we also have to add this guy who has 2 in both of the entries. Okay. So we would have 5 cases for X and S, which is exactly what we found, right? When we went back here and we were looking at how many possibilities we have for X and Y, for X and S, we found exactly these 5 cases. right here. These 5 cases, okay? And we now know that we could have figured it out more easily by all of this discussion that we made. I'm sorry, I'm going backwards. With all of this discussion that we made here, we now see how to figure it out more effectively. Okay, so in reality, all that we did here is we are, I don't know why it's not working correctly. We are just figuring out how many pairs of this form there exist that have in the first coordinate, they have all of the smaller numbers. So 0, 1, or only the smaller numbers. We double that to account for the mirror image, and then we add the last element, which is this guy right here. So overall, if we care about the number of pairs that we have, they are exactly 5 pairs, and we could figure it out without digging into the number. Okay. So this gives us actually the following formula. If you have a specific least common multiple that you're caring about, so we had, in our case, we had 2 squared times 30 to the first for 12. In order to figure out all of those pairs x, y that correspond to the powers of 2, you can just figure out how many pairs you have of this form. So how many pairs can you make where these numbers here are smaller than 2? How many pairs can you make? Just 2 pairs. Right, it is the pair 0, 2 and the pair 1, 2. There's nothing else that you can make. So then you double this number because you also have the mirror images. And then you add this guy. So if you have a power, if you have an exponent here, specific exponent in the prime factorization, then the possibilities for the pairs of exponents, x, y, are exactly this many, 2 times n plus 1. Okay. So, so I am running out of time, so I will do the next example. But for the next example, we're going to try to find the ordered pairs without actually finding out any of them ourselves. We're going to just try to count them. Okay. Okay. So, so let's look at this problem. We want to find how many ordered pairs we have, such that the least common multiple is 72. And we start with the prime factorization. Okay. Okay. So we saw that the pairs have a specific form. Okay. For example, when we're looking for 6, they look like 2 to the x times 3 to the y and so forth. Okay. So can somebody tell me what will these ordered pairs look like that have a least common multiple of 72? Can somebody try to tell me what they're going to look like? What is the format of the pairs going to be?
Can I try?
Yes, of course.
So, I figured out that 9 and 8 can be least common multiples of 72. So
Okay.
if we're going to do that in exponential form, we have to start with 9, which will be 3 to the second power multiplied by 2 to the power of 0.
Nice.
And for the 8, we're going to have to do, let's see, 2 to the third power multiplied by 3 to the power of 0.
Perfect. That is the idea. So what is the most general way that I can write these pairs? It's going to be 2 to the x times 3 to the y, 2 to the t times 3 to the s. Okay, same format we were working with. Okay, they're gonna look like this. All right. And then we just have to figure out what are the possibilities for x comma s and y comma t. Okay. So let's see. Can somebody try to tell me how many possibilities I'm going to have for x and s in this case? We made a discussion that x and s is going to be consisting of that x and s is going to be consisting of all the pairs that have smaller number here, and because we have a 3 up here, how many pairs like this can I make? Where the question mark can be smaller than 3. How many pairs can I make like that? So 0, 3 could be a possibility. What other possibilities could I have?
2, 3.
What? Repeat, please.
2, 3.
Yes, 2, 3 could be a possibility, of course. Right, and 1, 3.
1, 3.
Yes, because I'm looking for all the pairs that have a smaller entry here than 3, and they are at least 0. Okay, so I have all of these cases, actually. And I have also their mirror images. All right. So I have all of those pairs and their mirror images. And of course, I could also do 3, 3. Okay. So how many are all of those possibilities? So we have
Ordered or unordered?
we're going for ordered at this time, but
6. Or no, 7. 7.
yeah, 7 ordered pairs. Like, and the formula is the one that we discussed. You take the number that is in the exponent.
But if
Yes.
it was unordered, it would be 3.
If it was?
If it was unordered, it would be 3.
If it was unordered, yes, it would be 3. Yes, nice. But now we're caring about ordered pairs, for ordered pairs for these cases. So you see that we actually have 7 choices, right? For x and s, we can make 7 choices. And here you can see them. And if we can make 7 choices for those pairs, then exactly with the same idea, we can find the pairs for y and t. So how many what would be the possibilities for y and t this time? Now be careful because we have an exponent of 2 up there. So what would be the possibilities for this? So we would have, for example, 0, 2. What else? One, 2 could be a possibility. We're just looking for the first component has to be smaller than 2 and at least 0. Okay. So we have their mirror images as well. And we also have 2, 2. Okay. And so these are 5 choices that we have for this exponent. Okay. So we actually have 7 cases for the exponents for those pairs, x, comma, s. And here are the pairs. And we have five cases for those YT pairs. Okay. So now to find the number of ordered pairs, we're gonna see that they are 5 times 7, the product of this. Okay.
But if it was unordered, it would have 6 of them, since there's three of them are from the last one, and then 2 of them from this one would be 6.
Actually, since we have 35 ordered pairs here, to find the unordered pairs, what do I have to do? Do you remember the discussion we had at the beginning? You have to subtract the ones that have the same components and then divide by 2, right? So if you're going to do the unordered pairs, you could actually subtract 1 and divide by 2. Okay. Now, I want to stop here because this is a lot of information. And I'm going to briefly repeat the algorithm in the next session, okay? Before we start. But this is basically all of the idea of this technique is that instead of digging into the actual, instead of finding the actual pairs, we just try to find all the possibilities for those exponents that you see here. And this discussion that we made is how can you obtain these pairs? Okay. After you figure out how many of those you have, you just multiply them together. That is the idea. But I will review it briefly next time before the next presentation. Okay, so I'm going to actually stop here.